Hi everyone, we're going to continue with the content that we started in lesson 2. We just have a couple of points left to cover here. So in lesson 2, the last thing we were starting to discuss was the difference between what we call an intersection of sets and a union of sets. So what you're going to notice is that there are different types of notation that are used for intersections and for unions. So if you see A intersect B, so it kind of looks like an N a little bit. What that means is we're looking for elements that are members in both sets that are given. So if I want to know what A intersect B is, I would want to know which elements occur in both set A and set B. A union is very different. It's sort of like either or. If I say find A union B, and then again that looks a little bit like a U, what we want to know is which elements are members of set A or set B, and they actually could be in both sets A and B. So we're going to explore some questions in just a second on intersections and unions, but the symbols are super important. It's really critical that you know the difference between intersections and unions. The last part of this slide talks about sets that happen to be disjoint. Sometimes two sets don't have anything in common, and if that's true, we say that those two sets are in fact disjoint. So if I talk about the set of all even numbers and I talk about the set of all odd numbers, those two numbers don't share anything in common, so they'd be considered disjoint. So let's look at a couple of examples with this new notation for intersections and unions. So example 6 at the top of your slide is actually from page 12 in your workbook, so you can follow along there if you like. But what we're describing here are 4 different sets. The first universal set, so again, the universal set is where we're going to draw all other subsets from. The universal set are all natural numbers that are less than 20. So we know natural numbers start at 1 and we continue till we reach a value that is less than 20. So in this case, we have to stop at 19. So I'm just writing out this universal set to be super clear about the numbers that we have in mind. So it just takes a second to finish jotting these down. So there's your universal set. And then they have sets A, B, and C, which are already drawn out for us. So set A looks like multiples of 3. So we have 3, 6, 9, 12, 15, and 18, of course. We have set B, which is defined as multiples of 5, essentially. So 5, 10, 15. And then we have set C, which looks like multiples of 6. So 6, 12, and 18. So we're going to use these sets to answer all of the questions that you see at the bottom sort of portion of your slide. So part A says list the elements of the following sets and describe each set in words. So if I want to know what A intersect B is, what that means is I want to include any values that are both, or any elements rather, that are in both A and B. So they have to be in both sets. So if we look down the line, 3 is not common, so we're comparing A and B here first. 3 is not common, 6 is not common, 9 isn't common, 12 isn't common, but 15 is common. So we can say A intersect B shares the element 15. It's in both sets. So we would write that. I'll just get rid of my highlights here. We would write that and say A intersect B is the element 15. It's just that one number. So if we continue using those sets, part B is saying what is A union B? Remember, a union is very different than an intersection. A union means it can be in A or B, or it can be in both if you want. So A union B is going to have 3 in it. If we go in increasing order, 5 is in set B, so we would include that as well. 6 is in set A, 9 is in set A, 10 is in set B, so as a union it's okay to, or we have to include it. 12 is in set A, 15 is in both, so we can include it in our union, and then we have 18 as well. So that's basically that's your set A union B. Now we get into some complements. I just want to remind you that when you see an A with a little apostrophe, what that means is the complement of A. So what we're saying is it can't be an A, but it's everything that's missing when we compare to the universal set. So in a different color, right at the top row, I'm going to actually write out what not A looks like. So the complement of A, again, you compare against the universal set. So what we see in the universal set, but not in A, are the values 1 and 2. 3's in set A, so it's not part of the complement, but we have 4 and 5. 6 is in set A, so it's not part of the complement. We have 7 and 8. Essentially, it's everything but the multiples of 3. So not 9, but we have 10 and 11, not 12, but we have 13 and 14, not 15, but we have 16 and 17, not 18, but we have our last element of 19. So that's not A. What that's going to help us to do is answer the question that we see in part C. It says, I guess I'm not labeling these very well. Let's try and fix this for you here. My apologies. Let's fix the numbering. So this is part 1, this is part 2, and this is part 3. Part 3 wants us to find not A intersect B. So we're going to be looking at what's in not A and see what that shares with B. So what we recognize is that not A shares 10, but it also shares 5 with B, and that's about it. 15 doesn't appear in not A, so those are the only two in our intersection. So I'm going to clear those highlights so we can see those sets nicely again. But again, what we see in not A and B simultaneously is 5 and 10. So again, be very careful with intersections and unions, and if you're dealing with complements, I highly recommend you write out what that complement looks like and put all of the elements in that set so it's super clear. If I had to describe these sets in words, I know that A is essentially multiples of 3. I'm just going to write that here. And again, we're talking about natural numbers that are less than 20. Set B contains multiples of 5. And set C contains multiples of 6. We kind of were able to see that when we were writing out the elements in the set. So when we look at those and we need to describe these sets in words, if you have A intersect B, it means it has to be a multiple of 3 and a multiple of 5 as well. So we would say that this is a multiple of 3 and it also has to be a multiple of 5. When we look at A union B and we describe this in words, A is a multiple of 3, B is a multiple of 5, but union means the word or. So A union B means that this is a multiple of 3 or a multiple of 5. Now the last one is a little bit tricky. Not A means it can't be a multiple of 3, but it also simultaneously has to be B, which means a multiple of 5. So we would say in this case, it has to be not a multiple of 3, but it has to be a multiple of 5. So we would say it's a multiple of 5, but not 3. So I'm leaving all of my set information at the top here, but we're going to continue with part B, subsection 1, I guess. So if we want you to write the set that is equivalent to B intersect C, It means we're looking for elements that are common to both. They have to be in both because this is an intersection. So if I look at my list, nothing is shared between B and C when we compare those two sets. So what this means is these two sets happen to be disjoint. If there aren't any elements in common, you remember from a previous definition we looked at on Thursday that we have to say that this is actually an empty set. So there are a couple of ways you can write an empty set. You can either say 0 with a slash through it, which means there are no elements that are an intersection between B and C, or you can use set notation and have an empty set of curly brackets. So again, there is no intersection between B and C because nothing is shared for those elements. Now when we look at part 2, we want A union C. So what that means is we're looking at things that are in either A or C, or they can be in both. That's okay too. So we see that 3 is part of set A, 6 is part of both of those sets, 9 is part of set A, 12 is part of both of those sets, and then we've got 15 as part of set A. We have 18 as both or elements in both of those sets. So that would be basically our set that is equivalent to A union C. Now in part 3, we're changing that union to an intersection. So if I say find A intersect C, we're looking for things that are common between A and C. So 6 is common. That's one of our elements in the intersection. We also see that 12 is common as well. And we see that 18 is common. So the intersection between A and C would include 6, 12, and 18. So I'm just going to get rid of my highlights here so we can rewrite that set. It's 6, 12, and 18 in the end. Now in part C, we actually have the introduction of a new set. We're saying set D is defined as 2, 4, 6, 8, 10, 12, 14, 16, and 18. So if this is a newly defined set, subset 1 says find A intersect B union D. Now that B union D is in brackets. So what that means is we first have to find B union D, which means numbers that are in set B or in set D. And then we have to find that intersection with set A. So this is going to take a little bit more work. The first thing I want to do is actually define B, or to find B union D. Again, that's a union, so it means it could be in set B or in set D. So what would happen in this union is we would have 2, 4, 5 is in set B rather, 6, 8, 10, 12, 14, 15, 16, and 18. So that's the union between B and D. So that's B union D. But now we actually have to find an intersection. So we want to intersect between A and the new union that we just created. So we need to look for common threads between A and B union D. So let's highlight those. If I look at subset A, we have a 3 and we have a 6, which is common to both of those. So that would be an intersection. 8's not common, 9's not common, 10's not common, but 12 is common. 15 is common, and 18 is common. So those would be the intersections between those sets. 6, 12, 15, and 18. So we would write those very carefully. So again, we have 6, 12, 15, and 18. So again, this took a little bit of extra work because we first had to find B union D. In part 2, we're asking for something very different. Once again, we're saying find A intersect B, and then find that with a union, or find a union with that and D. So once again, with what we have in brackets here, we have to first find the intersection. So A intersect B really means we need to find what's in both A and B. So A intersect B has 15 in common. And that's it. So A intersect B is done, but now we have to find A intersect B union D. So what that means is it has to be in our intersection between A and B, or it needs to be in set D. Essentially, if you look closely, it's basically going to be set D with one additional value. We're going to throw 15 in that mix as well. So 2, 4, 6, 8, 10, 12, 14, 15, 16, and 18 would be the elements in A intersect B union D. The last one we have here, part 3, basically we've got a whole bunch of complements here. We have not A intersect not B, but then the complement of that intersection. So already, and we've left the work at the top of the screen, we found not A. It's important for us to find not B as well. So if B is 5, 10, 15, not B is anything in the universal set that's not contained in B already. So we've got 1, 2, 3, 4, skip 5 because 5 is part of set B, 6, 7, 8, 9, not 10, 11, 12, 13, 14, not 15, 16, 17, 18, and 19. So now we need to find the intersection between A and B. So we're not doing the whole question at once. We're just saying let's focus on not A and not B. So the intersection between these two complements, if we take a look at our list, 1 is shared between them, 2 is shared between them, 4 is shared between them, and the list goes on. So we've got 1, 2 shared between those two complements, 4 is shared between those two complements, 6 is not shared, but 7, 8, 9, 11 is shared, not 12, 13, 14, 16 is shared, 17 is shared, 18 is not shared, but 19 is shared between those two complements. So this is not A intersect not B. So that's what's shared between both of them. Now what we need to do is find the complement of that. So if we have not A intersect not B prime, what it means is anything that is in the universal set but not in not A intersect not B. I know it seems really confusing, but if I look at my comparison, I'm actually just going to cross things out to make this visually easier for you. Remember, a complement means it's not part of the universal set. So from here, 1 is part of the universal set, so it's not the complement. 2 is in the universal set. 4 is in the universal set. 7 is in the universal set. 8 is in the universal set. Whoops. 9 is in the universal set. 11 is in the universal set. 13, 14, 16, 17, and 19. So all I have left in my complement is 3, 5 and 6, 10, 12, 15, and 18. So this is going to be the list of elements. So 3, 5, 6, 10, 12, 15, and 18. These got quite complicated, so what I highly recommend is that you are very explicit and write out your sets clearly, so it's easy for you to do things like find intersections or unions and complements as well. So what you've recognized is that I've actually written out those complementary sets so that I can make my comparisons more easily. So at this stage, we're finished with lesson 2. So please have a look at the regular homework questions that are assigned from page 12. I am going to continue our discussion now in this video lecture on lesson 3, which is going to take a slightly different look at how sets can work together or can be depicted in the same kind of graphic. So to start lesson 3, it's actually the first part of our deep dive into what's called Venn diagrams. So a Venn diagram is really a visual representation of how sets fit together, or maybe how they don't fit together. So you see a Venn diagram actually on the slide in front of you. It says let S, so capital S, is the set of students in a specific class. If that's true, then we're going to let capital F be the set of those students who identify as females in the class. So those females are a subset of all of the students in our group or in a classroom. So we want to show you how sometimes these circles can overlap, sometimes these circles are going to be separate. It really just depends on the situation that we're given. So we're going to take a look at our first example and play around with how to draw these Venn diagrams properly. So example 1 here says, consider the following sets and create a Venn diagram. So we want to have a big rectangle with circles inside it to denote the behavior of the sets that were given. So set U, the universal set, are the natural numbers that are less than 11. So the universal set, if we write out those values, and this is going to be extremely helpful, are going to start at 1 and increase to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Again, it's strictly less than 10. E is going to be another set, a different set, and these are natural even numbers, less than 10. So they're still natural, but they're even numbers less than 10. So we're talking about less than 11. 2, 4, 6, 8, and 10 are going to be our set elements in E. So M is being defined as the natural multiples of 3 that are less than 11. So when we look at multiples of 3, a multiple of 3 would be 3, 6, 9, and of course 12, but that goes too high because we're talking about natural numbers that are less than 11. So we've got 3, 6, and 9 as elements in set M. If we want to draw a Venn diagram, we have to decide with a rectangle. So the rectangle is sort of the boundaries for our universal set. We have to decide, and you can put a U on the outside because we know that marks our universal set. We have to put all the numbers 1 through 10 inside this universal set. But we have to be careful because some of those numbers belong to E, which are the even numbers, less than 11. Some of those numbers belong to M, which are the multiples of 3, and some of them actually involve both of those sets. So if we look for an intersection, what I want you to recognize here is that 6 is an element in both of those sets. So when I draw a Venn diagram, I'm going to have subset E, I'm going to have subset M, and I'm going to have a point in between them overlapping because there are some numbers that are going to exist in both places. So let's put every number where it belongs. I can see that 6 is common to both. It's an even number and it's a multiple of 3. So I'm going to put 6 dead center. That's right in the middle. Now I'm going to keep filling in all my even numbers. So my even numbers were numbers like 2, 4, 6 is already covered, we have 8, and we have 10. So those are my even numbers. My multiples of 3, we've got 6 in there already, but we have 3 and we have 9 that are outstanding. So what you notice is that everything in circle M are the elements in set M. Everything in the circle E are the elements in set E, but those two circles overlap because we have an intersection with the element 6. Now we're not done with our diagram yet because anything that doesn't fit in E or M, but happens to be part of our universal set, needs to float around the outside. So what I recognize is 1 hasn't been accounted for yet. So 1 is part of our universal set, but it's not even or a multiple of 3. 2's already been taken into account. 3's already been taken into account. 4 has already been taken into account. But we have 5 that's outstanding. 6 is a multiple of 3 and an even number, so that's done. 7 has not been documented anywhere. 8 is an even number, so that's been taken care of. 9 is a multiple of 3, so that has been taken care of. And 10 is an even number, so that's already been written. So what I want to see in this Venn diagram is every single number that we have in our universal set, but put in a position where it belongs. So is it even? Is it a multiple of 3? Or is it floating outside because it's not even or a multiple of 3? So the next slide gives us an opportunity to shade in diagrams based on whether we see intersections, unions, or complements. So we see a picture that has been given to us. There's a universal set U, and then there are subsets of A and B. And we can see that A and B have some overlapping elements, so they have intersections between them. What our instructions are, in this case, are to shade the regions that represent each of these notations. So the first part A, says shade in what A intersect B looks like. So what region would A and B have in common? We're looking for elements that are shared in both A and B. So if you were to shade that part of the diagram in, this is what I would be looking for. I would only want you to shade in those overlapping parts for those separate sets. So that would be A intersect B. Part B says instead of an intersection, what would it look like if you shaded in the union? So in your mind, what I hope you're remembering is that a union means it could be an A or B, or in fact, both of them. So if I shade in, kind of went out of the line, so I'm not a great colorer on these things. So we've got A union B, which means we have anything that's in the subset of A or the subset of B, or in fact both. So that's the difference between A intersect B and A union B. The last thing we want to shade in part C says, what does not A look like? So basically, this is the complement of A. What I hope you do in your mind for complements is you sort of think to yourself, okay, A is the stuff inside the circle. Not A is going to be everything outside of that. So we're going to shade everything in the universal set. We're going to shade everything that's not overlapping in B. So again, forgive my bad coloring here. But we're shading in everything that is not in A. So if we're really clear about what not A looks like, what we should see is a bright spot inside circle A. So everything outside of A should be shaded because everything outside of A is that complement of A. So once again, these activities are for you to sort of wrap your head around what intersections, unions, and complements look like when we start shading in or utilizing these Venn diagrams. At this point, we want to take a look at example number 3, but it's actually a class exercise. So in page 20 of your workbook, you see a whole bunch of Venn diagrams where they're asking you to shade. What I want you to do is try and shade what they are asking for. So they might be saying, find not A or find not B, and shade in as we've done in this previous set of exercises. So please have a look and try those. I want you to pause the video now, and I will be uploading the solutions for you to check your own work in Blackboard. So have a look at page 20, shade in those examples, and make sure that you understand what's being shaded for each of those descriptors. Hopefully you worked through some of these activities, and you can see here that I've taken a photo of the answer key. I will be uploading this to Blackboard as well, so you can pause the video here and check your work. But what I want to show you, or just make sure I'm highlighting here, is that the first example asked you to shade set A. So we know that that in this case, all of the shading is inside bubble A, but they're also asking at the bottom for you to determine the number of elements in A as well. So if you were to count the number of elements that are happening in A, and it doesn't matter if it's overlapping with B, we just want to know how many elements are in that first circle or circle A. In this case, we see there are 6 of them. When you move to the next example, it says shade in set B. So you're shading in everything inside circle B. And then at the very bottom, it says, okay, how many elements are in B? So if you counted the numbers or the values, elements inside set B, you would see there are 3 of them. So once again, give the video a pause and make sure that you have all of these answers correct, and put a star beside anything that you're having trouble with, and we can come back to it when we reconvene on Monday. But we're going to continue on to our next example here. If it's easier for you to continue working in your workbook, we're going to take a look at page 22. So you have another Venn diagram. We see that there's a universal set U, and then there are 2 subsets that we call P and Q. So they're overlapping. What we want to do is answer all of the questions that follow here. So with 4A, we want you to list the elements in set P. So it doesn't matter if they're overlapping or not. And I like to put these in increasing order. So 1 is the smallest element, then we have 2, we have 8, we have 9, and we have 10, because those are all the elements inside that bubble for P. Now we want to find in part B set Q. So Q contains 1, 7, 10, and 29. These numbers seem to be a little bit more random, so that's okay. Again, these sets and subsets were predetermined with this question. Part C says find P and Q. So to write that in a different way, remember that's an intersection. So if I wanted to find P and Q, or the intersection between those two, you could look at the way we wrote out the sets and find anything in common, or you can look at the diagram. What we recognize is that 1 and 10 are shared by both sets. So you could check that both ways. So P and Q includes 1 and 10. That's shared between them. Now in part D, it's changing things up a little bit and saying what's in P or Q. So we can use a union in this case. So we can list the elements that are in set P or set Q, or in both. So we've got 1, we have 2 that's in 1, or again, both. Here we've got 7, we have 8, we have 9, we have 10, and we have 29. So those are the elements that are in set P or in set Q. Next, we have to worry about complements now. So they're saying which elements are not in P. So this looks like P prime. So if I can imagine that P is anything inside this circle, not P is anything outside of that circle, but be a little bit careful, because if it's part of the universal set, we must also include it. So on top of having 7 in our complement of P, we also have 11 outside of that circle. We have 16 that's part of our universal set that's outside of that circle, and we have 29. So again, we're looking for the complement of P in this case. Same thing is going to happen for not Q. So not Q means the complement of Q. So I'm going to erase this and just change my diagram a little bit. So if everything inside the circle is part of Q, not Q is everything outside of the circle. So here we've got 2 as an element outside the circle. We have 8, we have 9, we have 11, and we have 16. Again, you can do this using our Venn diagram, or you can do this visually, or not visually. We can inspect the actual sets themselves and get exactly the same answer. Part G is going to take a little bit of work as well. So if in this case we want not P and not Q, we can write it like this. So not P or the complement of P and not Q. So good thing is we already have not P and not Q right above in parts E and F. So if we find the intersection between those two sets, what we recognize is that 11 is common to both of those. So we can circle that or highlight that for now. 16 is also common to both of those. So not P and not Q would be both 11 and 16. So let's finish writing that properly and list those elements the way we should. Now in part H, it's slightly different. This is a union. So we're saying what's in not P or not Q. So it doesn't have to be common to both. It just has to be in one or the other. So if we look again at not P and not Q and focus on those two sets, we've got 2, 7, 8, 9, 11, 16, and 29. So again, it can be one or the other, or in fact both. So with part I, it says what is not P or Q. So if we have P or Q and we say not those things, sometimes it's easier just to highlight. So what I'm going to highlight is P or Q. So if it's in P or if it's in Q, it's going to be highlighted. So these are the parts of the set that we're thinking about for P union Q. So if it's not that, we can see very quickly and easily that that set is going to be made up of 11 and 16 because those are outside of the highlighted regions. So I highlighted P or Q and we want not that. So we want anything in the universal set that's not highlighted. We can take the same approach for the last question here, J. So it's saying not P and Q. So if you think about P and Q, we're the intersection between those, and then we want the complement of that. If I highlighted P and Q, it would be the overlapping parts of those two circles. So if we want the complement of P and Q, it's everything that is not highlighted. So we would start with 2, we have 7, 8, 9, 11, 16, and 29. So Venn diagrams can be a really nice way for you to shortcut some of these activities. Our next example for practice is the diagram below displays the number of students who are members of either the Students' Council, and that's denoted with an S, or they're members of the yearbook committee, and we say that that's Y. So we've got two subsets as part of our universal set. The first question we're asking you to do is figure out how many students are on the Students' Council. So if I highlight Students' Council, we're highlighting anything included within that circle. So if I know that there are 12 students on Students' Council and 3 who are also on Yearbook Committee, 12 plus 3 is going to give us a total of 15. So there are 15 students. Oops, that's in the wrong spot. Let's fix that. We've got 15 students that are on Student Council. The next question says how many students are on both Student Council and the Yearbook Committee. So this is an intersection. The intersection between Student Council and the Yearbook Committee is right in the center, and we see that there are 3 students in that position. So the answer to part B is in fact 3. So there are 3 students on both. Now part C says how many students are on the Yearbook Committee but not Student Council. So what we want to highlight here is Yearbook Committee, but we want to avoid any overlaps with Student Council. So this is the area that we're thinking about in terms of the Venn diagram. And what we see when we highlight that circle is there are in fact 7 students that are on Yearbook Committee but not on Student Council. So the answer for part C is 7. Last question. Let's just erase these highlights so we can start fresh. Last question, how many students are on Students' Council or Yearbook Committee? So this is a union, which means we're going to count everybody inside both of those circles. So we know we've got 12 plus 3 is 15. 15 plus 7 more is going to be a total of 22. So there are 22 students between student council, and the yearbook committee. So our next example reads, in a homeroom of 20 students, so we have 20 members in a universal set, 15 take math, 12 take social, and 10 take math and social. So we need to show this information in a Venn diagram. So what we need to realize first is whether or not there's overlap between students in math and in social. And of course there are, because we know that 10 of them take math and social studies. So if we draw our circles, again, one of them is going to illustrate what's happening with math. The other is social studies. And actually, I'm going to put that M right inside the circle. So this is math. We have S for social studies. And what we know is that 10 students take both. So we're going to put 10 right in the center. Now, this is where students can sometimes get confused. We have a total homeroom of 20 students. If 15 students are taking math, it is impossible for us to put 15 in that outer part of our circle that's not overlapping, because that would mean we have 25 students. So we know that that's not correct. Basically, what we need to have here or manage is a total of 15 students taking math. So if we know that 10 students are taking math and social, then there must be remaining 5 that are taking exclusively math without social studies. The other piece of information we were given is that 12 students, in fact, were taking social studies. So 10 of them are taking math and social, which means an additional 2 students are only taking social studies. So we know the 10 that's overlapping plus the 2 that's in that social studies bubble in our Venn diagram give us the total of 12 for social. Now we're kind of missing something here. We know that the universal set on the outside has to have a total of 20 students. If I add up the members inside those Venn diagrams, 10 and 5 is 15, 15 and 2 more is 17. So we only have a total of 17 students that are taking math or social. What that means is we have an additional 3 students that aren't taking any of those subjects. So when you fill in your Venn diagram, be careful about filling in every single option. So not only do we have math and social to contend with, but we have remaining students who are taking none of those subjects. So this would be your Venn diagram for example 6. The last example in this section actually carries over 2 slides, so I've got them both posted here for you. In example 7, it says, in a survey of 400 households, 285 had a personal video recorder, so PVRs. 320 in those surveyed had multi-functioning printers, so we are calling those MFPs. What we also know is that 63 households did not have PVRs or MFPs. Let P represent the set of households with PVRs, let M represent the set of households with MFPs, and let X be the number of households that have both. So what we want to do is build a Venn diagram with the information that we've been given so far. So in our Venn diagram, we know that there are some households that have both M and P. So they have multifunctioning printers and they have PVRs. So when we draw your Venn diagram, we have to have overlapping pieces. We also know in this case that we've got 400 in our universal set. Now that doesn't mean that there are 400 sitting outside of our circles. It means we have a total of 400. Now, if we don't know how many people have both, what we need to do is choose a variable. And in this case, it's saying let X be the number of households that have both MFPs and PVRs. So we're going to put an X dead center here because that's the overlap. We have multifunctioning printers on one side and we have PVRs on the other side. Now, if we go back to the information that we were given, we can actually label some more parts of this Venn diagram. From the beginning, it said in a survey of 400 households total, 285 of them had PVRs. Now be careful, it doesn't mean that 285 sits outside that overlap. It means we have 285 in total. So what we need to do is subtract that overlapping piece. So that part of the circle is going to be a total of 285 minus the overlap, because we can't count those people twice. So for example, if we had 10 people, just hypothetically speaking, if we had 10 people that had both multifunctioning printers and PVRs, then 285 minus 10 would be a remaining 275 people who just have multifunctioning printers. The second piece of information talks about PVRs, and it says a total of 320 people had PVRs. So we know that that 320 isn't exclusively outside the circle, but it has to be 320 minus the overlap. So 320 minus X. We don't want to count those people in the middle twice. Aside from that, the only other numeric piece of information we were given says that 63 households didn't have either one. So that 63 needs to sit outside of those circles because they're not part of any of those sets or subsets. So if we take a look at the next slide, it's asking us to do a whole bunch of things. It says mark X and 63 in the appropriate parts of the diagram. Well, we've already done that. X is the overlap, and 63 is going to be sitting outside in that universal set. So part A is finished or complete. Part B says to write an expression for the number of households who have a PVR but not a multifunctioning printer. So if we're looking at that area, the people who have a PVR but not a multifunctioning printer would be this group on the outside. And we've already specified that that group is 320 minus X. So we'll just delete that. In part C, they want us to write down the expression for the number of households who have multifunctioning printers but not PVRs. So they're looking at this side of our Venn diagram. So we don't want to overlap with PVRs because that's what they're saying. They don't have PVRs here. So we know that that's going to be 285 minus X. And in part D, they're asking us to build an equation. They're saying form an equation in X and determine the number of households in the survey who had both. So basically, this is an equation for us to solve. The only piece of information given to us originally that we haven't accounted for is actually the grand total. We know that there were 400 households surveyed. So if I take each and every one of these elements and I add them together, I'm going to get a grand total of 400. So let's go ahead and do that. If I take 285 minus X, which are the number of people who have multifunctioning printers but not PVRs, if I add that to the overlapping middle section of X, because those people have both devices, if we add that to the folks who have just PVRs, so 320 minus X, so again, we're accounting for all of those elements inside those circles of our Venn diagram. If I take that and I add the 63 people that don't have either type of device, what I know is I'm going to get my grand total of 400 households surveyed. So this is just a matter of solving this tiny little equation. I know it looks messy, but it's quite a simple equation once we open up the brackets. So 285 minus X is going to stay that way. We're not distributing any fancy signs or anything in the front. We're going to add X, we're going to add 320, and we're going to subtract X and add 63 to give us the grand total of 400. This is when we can go through and collect some like terms or put some things together. So if I collect my X's, those two X's cancel. Actually, let's use a different color to show you that. This X cancels with this X, and what we're left with is negative X on that left side. Now we can go ahead and combine some of our terms. So if you take 320 and you add 285 because that's a constant, you can also add 63. So we're adding these three terms to get another grand total of 668. If that's now equivalent to 400, this is a pretty easy equation for us to solve. What you can do is push the 668 over to the opposite side by subtracting. So we have negative x equals 400 minus 668. So we get negative x is equivalent to negative 268. But we want to solve for positive x, not negative x. So you can multiply or divide both sides by a negative 1. What that means is x is equivalent to 268. So what this is telling us is that 268 people have both devices. We could answer a whole slew of other questions from here. I could say, how many people only have multifunctioning printers? And you'd go 285 minus 268. So you'd see that only 17 people have multifunctioning printers alone. Again, you can answer a whole host of other questions from here. This is probably the most challenging type of Venn diagram that you're going to encounter, because here we're asking you to build some equations. What I want you to be mindful of with these examples is when they give you a total for things like M or things like P, you have to account for the overlap, and you don't want to count those people twice. So in this case, we had a little bit of subtraction to make sure that those folks in the middle weren't counted twice, or those households in the middle weren't counted twice. All right, everybody, that's the end of lesson 3. If you want to tackle some of the homework questions, please take a look at page 23 in your workbook and try numbers 1 through 12. When we meet again on Monday, we'll discuss some of these elements and make sure that everybody's on the right track before we get too carried away with lesson 4. Hope you had a good weekend.